prospect total property measurements at Belle II by Dr. Michel Hernandez Villanueva. Okay.
Hello, just to confirm,
start.
Can you see my screen?
Yes.
Okay,
Please
thank you very
start.
much. Yes. So it's for me a true pleasure to present the status and prospects for trout property measurements on behalf of the Belle II Collaboration. There are several things to discuss, so let me quickly introduce the accelerator, which is SuperCakeB. This is an upgrade from the former CakeB accelerator at KK in Japan, which has the main feature that it increased the integrated luminosity 40 times more than the previous B-factories, or that's the goal of the design. And the way that this is achieved is using the nanobeam scheme, which is basically to squeeze the beams and the interaction point without the need to increase the currents. And that will increase the peak luminosity that will help us to reach this large integrated luminosity expected, giving us all this huge data set. Belle II, it's the detector who is located at the interaction point. It's SuperCakeB. And let me just comment that this is not for free. There are some challenges that we need to attack at this high luminosity. One of those is the higher background rates. So we expect to have more radiative VAVA, Touchek, etc. events that makes difficult to extract the signal from the different events that are recorded. And the other thing is that we expect higher trigger rates. So that means that we would require an upgrade in all the part of the DAQ and computing and so on. So for that, the Belle II Collaboration is the group that is tackling all these challenges. We are now more than 1,100 members in 123 institutions around 26 countries. So this is just a diagram of where Belle II is located with the accelerator SuperCakeB at the laboratory KK in Tsukuba, Japan. So if you have visited KK, or if you have the chance to visit KK once, you will see the Mount Tsukuba at the back. It's a really nice place. And this is just a picture of the collaboration just before the rolling of the detector, before the first collisions, in which, well, you can see just a few of us. But of course, we are not all the time together. Usually we are a quite distributed collaboration. This is a challenge itself, but it's also a strength of our own collaboration because we have a truly international effort in the different challenges that we have to tackle. So speaking of the experiment, there are new features with respect to the previous B-factory Belle. The main ones that I can highlight is that we have a new vertex detector with 2 additional layers of depth technology plus 4 layers of SDD. With that, increase our capacity during the reconstruction of the vertex, the vertices during the decay of the particles, so the resolution is much better. We have 2 new detectors which are dedicated for the particle identification, one in the barrel region and one in the end cap that use the Cherenkov radiation for the identification of the nature of the tracks that are passing through the CDC. And of course, we also have the electrocalorimeter, the outer layer, which is dedicated to the detection of muons and K-longs. The readout, it's completely new. It's dedicated to reach 30 kilohertz in the L1 trigger and approximately has 100% efficiency for hadronic events. This is not the case for the tau lepton pair, so I will discuss that later. Also, our software, I would like also to highlight that it's now open source. It's available if you want to take a look on that. And it contains sophisticated algorithms for the simulation, reconstruction, visualization, and analysis of the different events that are reconstructed. And for the offline computing, now we have it's distributed around different sites on the world using the grid. This increases our capacity of the data reprocessing and also the production of the Monte Carlo, which basically means we will have higher statistics during the studies. That reduces the statistical uncertainties. Let's talk about what is the status, how much data do we have. During this time, we have collected around 200 inverse femtobarns. And I also would like to highlight that despite the global pandemic, we have reached the super big factory performance level, breaking the records that are listed here. So as you can see, just at the time that the luminosity started to ramp up, we had this unfortunately global pandemic that affected us all. However, thanks to the effort of the collaboration of a social distancing scheme in the contribution between the people who is on site and the distributed remote shifters, we have been able to collect these 200 inverse femtobarns, breaking the records again that are listed. Also, we have reached the integrated, the peak luminosity of 3.1 times to 10 to the times 34, which is recently highlighted into the different publications available of high energy physics, which is also something remarkable using the nanobeam scheme that has become quite important, and this is a proof that it actually works. What are the projections talking about the future? So we have different milestones. By the next summer in 2022, we expect to collect 500 inverse femtobarns. And after that, by 2026, during the upgrade, just before the upgrade of the interaction region, we expect to collect of the order of 10 inverse attobarns. And at the end of the experiment, around 50 inverse attobarns by 2030 that will provide the large data set that enable the capacity to reduce the systematic uncertainties. Now, the program of Belle II, it's quite extensive. It covers measurements in BDKs, in charm, in dark sector, searches for exotic particles, etc. All the details about this program, you can find it in the Belle II physics book, which has been available for a while in this publication. You can take a look. And also to remark that this enormous number of electron-positron collisions features a unique environment for the study of tau physics with high precision. So I will focus on this part of this diagram. So talking about the tau at Belle II, so if you compare the cross-section of the production of the BB bar with respect to the production of the tau pair in the collision of electron-positron, the cross-section is of the same order. Then it means that the B factories are also tau factories. We produce approximately 1 million tau pairs per femtobarns. And given the characteristics of the B factories that we have a well-defined initial state, high vertex resolution, as I mentioned before, excellent calorimetry and sophisticated particle ID, this provides a great environment for the study of tau lepton decays. And the proof is all the very interesting results that the B factories Belle and Babar keep providing at the date, and we expect that most of the results will be updated with a Belle II dataset. So speaking of the future, there are few contributions during this conference by Belle II. I invite you to join us to all of them. So tomorrow we will have searches of indirect and direct searches of new physics, things related to lepton flavor universality at Belle II, and searches for the direct decay of a tau to an alpha invisible particle that could be interpreted as a candidate for dark matter. While on Friday, we will talk more about the precision measurements in the lifetime and the mass of the tau during the poster session that we also invite you to join. And at the end, in the final session, the future directions on tau physics and prospects in beam polarization. So please join us, all the different contributions. This is a diagram. Well, this is the even display of how it looks at tau decay in our detector. So as you can see, it's a quite clean environment. There is one of the taus decaying to 3 tracks, which we can identify as pions, and one track on the other side, which interacts with the outer layer, which gave us a very good confidence that this is a muon. Also, this is the signature of a tau decay that decays in one side leptonically, and on the other side to a hadronic decay of 3 pions. So again, this is quite clean environment, and it's just to illustrate the capacity of Belle to reconstruct tau pair decays, tau pair events. Of course, it's very important to know the performance of the detector. And something that I would like to share in this workshop is that the tau pairs are not only tools for the comprehension of fundamental physics, as discussed by our previous speakers, but also for the understanding of our detector. So, for example, we can study tracking efficiency using tau pair events. Given the characteristics of the tau, if you are able to identify this as a tau pair event using a tag, an electronic tag, for example, then you just need to identify 2 tracks to have quite a good confidence that there must be a 3rd track on the event. Therefore, it's possible to estimate what is the tracking efficiency, but most important, to have a good comprehension of the inefficiencies between the data and the Monte Carlo when you compare them. So this has been performed in Belle II, and the result has been provided to the collaboration. It's very important because this translates directly to a systematic uncertainty associated in which one of the results that will be provided by Belle II. And in the same way, we can study the lepton ID performance. So in Belle II, the particle identification is based on global likelihood ratios, in which the information of all the subdetectors is combined, and then the likelihood ratio gives a probability of a particle being of a quite depending on the nature that you are trying to identify. So with the same idea, if you identify two pions, well, after you tag that this is a tau decay, if you identify two pions of the same sign, you have a very good confidence that this is also a pion. Otherwise, the decay with a kaon is heavily suppressed. And therefore, with this pion, you can study what is the performance of the pion identification in the detector. So this has been also reported, and you can compare the result coming from the taus with the result coming from other decays that are also usually well used for the study of the identification of electron of muons. And this will be also very important in the future because, again, it's translated directly to systematic uncertainties. And finally, we have studied also the trigger efficiencies, which are very, very important since they are the ones that decide who are the events that we store. And of course, we need to keep them as many as possible. So the level 1 trigger efficiency has been studied using these tau pair leptons with 1-1 and 3-1 prong topologies. That means depending on the number of tracks in each one of the hemispheres of the event. As you can see, the full track trigger, that basically means the tracks that reach the barrel region present low efficiency in end caps. And additionally, the CDC also searches for short tracks. That means that they only reach the inner layers. And this provides a significant gain in efficiency for end caps or tracks with low PT. However, for one prong, this is still not enough. We have quite inefficiency in that regions, and this will be discussed by Alberto on Tuesday when he talks about the lepton flavor universality at Belle II, because these events are quite important. And I would like also to mention that there is some development that is already in operation, the single track trigger. This is a unique feature of our detector. It's a neural net based trigger that it's now operational. It fires if it finds a single track within 15 centimeters from the collision vertex, and it has a momentum larger than 700 MeV. So this is just the event display of one of these events in which just with a single track, we are able to fire the trigger and store the event. It's a unique feature that will allow us to improve the efficiency, especially for events of 1-1 in the end caps. The first results are coming with very promising results, and we hope to be able to show them very soon to all of you. Now, moving on to the measurement of the tau properties. This is just the diagram of the canonical test of the lepton flavor universality. There are quite a few quantities here involved that you can identify. That's the tau mass, the tau lifetime, and the leptonic branching fractions. And Belle II has the potential to provide precise measurements of all these parameters. So I will talk about the first two. And if you are interested in the topic of the lepton flavor universality, again, I invite you to join us on Tuesday. But for now, let's focus on the measurement of these properties. The tau lepton mass has been already covered at the beginning by Professor Peach, so I will be just quick on this. Let me just show you how this is put in the way that you can see the dramatic difference between the precision in the measurement of the mass of the electron of the muon with respect of the tau. This is, of course, of the lifetime of the particle, which does not allow us to use the techniques used for the other two. And there are two techniques, or basically two methods to measure the mass of the tau. The one presented in the previous talk by Lou Tau, that is the production threshold, in which the BES3 experiment has the best precision at the moment. And there is also the pseudo mass distribution, which was used for the first time by Argus, and it was also used in Opal, Babar, and the Belle collaboration, in which they hold the best precision with this technique. And the feature is that you don't have to be near the threshold of the tau production, but you can also make the measurement of the mass far from the region, and this will be exploited in Belle II. So the pseudomass, just to briefly describe it, it's a technique that uses the decay of the tau to 3 pions, in which, well, if you take the kinematics of the event, the mass of the tau can be calculated using the expansion of the sum of the 4 momentums. But as the direction of the neutrino is not known, the neutrinos are not detected in the different layers of the experiment. The approximation of that the cosine of the direction of the neutrino with respect to the direction of the hadronic system equal to 1 is taken. And this results in this very useful quantity that has the feature that is always lower than the true mass of the tau. Then the distribution of this quantity, the pseudomass, presents the feature that at the region, close to the region of the true mass of the tau, it has a sudden drop, and we can use such distribution to measure what is the real mass of the model lepton. So this is fit to an empirical ETH function, and the position of the cutoff indicates the value of the mass. Then we did this at Belle II the last year. This has been one of our benchmark tests of our capacity of reconstructing tau leptons at Belle II. And our latest result with 8.76 inverse femtobarn, it's the one that is quoted here, in which I can highlight that this is still statistically dominated. We have 2 main systematic sources. The first one is a momentum shift to imperfections of the B-field map, and the other one is a bias in the estimator of the m tau. This is just how it looks, the pseudomass distribution when we compare the simulation with respect to the data, and this is the sum, assumed in the region in which we perform the fit, using this PDF as an edge PDF, in which we can use the P1 as an estimator to extract the mass of the tau. And as
You have 4
I mentioned
minutes
it,
left. 4
okay,
minutes.
I will 4 minutes. Okay. Then I will move faster. I would like to highlight that we have currently a systematic uncertainty of the order of what was reported by Belle at the time, and we expect a significant reduction in the systematic uncertainty in the next result that we are close to publish. If you want to see more details, I invite you to join us to the poster session on Friday. Now, moving on to the lifetime measurement, sorry, I will be a bit faster. This is also important standard model parameter, and the most precise result has been reported by Belle, in which they use a three-prong topology with both leptons decaying to 3 tracks. And this is the result that is reported, and please be also notice that this is dominated by the statistical uncertainty. In Belle II, we can exploit the tandem beam scheme that I have been mentioning several times. The idea is to reconstruct the 3-prong vertex and then just use a kinematic constraint to determine what is the direction of the tau using the interaction point and the vertex that is being reconstructed, and with that determine what is the decay length. Given that we have an uncertainty in the y component of the beam of the order of nanometers. So when we perform this, you can extract the lifetime knowing the proper decay time distribution. And at this moment, when we do the study of in Monte Carlo, we obtain this result, which contains the same statistical uncertainty of Belle, but in this case, we are using 200 impulse femtobarn with respect to the 700 that were used by Belle. So this is a quite important improvement, and the reason is because we are using just 3-prong decay in one direction, while in the other side, you can use anything to tag the tau lepton. There are further studies that we need to consider to estimate the systematics, especially the vertex detector alignment. That was the dominant contribution during Belle and Babar when they performed this measurement. And just to compare the performance of the detector in these measurements, just want to comment also that when we are doing the studies in the Monte Carlo, the Belle II shows that we have a better resolution in the proper time of 2 times approximately. This is thanks to the PXT, and since we have a smaller beam pipe diameter. So as you can see, this is the distribution of the resolution of the proper decay time reported by Belle in the line, with respect to what we are observing in the simulation at Belle II. And one way to confirm that this is actually the case, because this is at this moment this is just a simulation, is that we can compare with the D-meson lifetime that was recently published, in which it's clear in the negative region of the property K-time distribution that the resolution at Belle II, it's quite improved with respect to Belle and Babar when you overlap the distribution that were reported by the different experiments. So if you want to take a look at this result, there is also here the archive that this has been submitted to PRL, and we hope that it will be published soon. If you want to know more details, again, please join us on Friday. During the poster session, there is a discussion on about the lifetime measurement at Belle II that we expect it will provide quite an improvement with respect to Belle. So that goes to my summary. In Belle II, we have reached this, SuperClickB has reached this new record in the peak luminosity that was highlighted in different publications around the world. We have collected more than 200 inverse femtobarns of data, and by summer we expect to collect of the order of the data set of babars. So that means that the results will be coming. And just to highlight that since its discovery, in the tau lepton has been studied at every new electron-positron collider into operation. That has been improving the measurements with every upgrade, and it's our turn in Belle II, and we are very well motivated and ready to reach new limits in the precision. We have been working hard to understand the detector and to provide all the performance that is required to quote the different uncertainties associated. And there are some studies about the mass of the lifetime that also will be discussed during the poster session. So I invite you to join us. And that's it for my side. Thank you very much.
Okay, Michelle, thank you very much for a very interesting talk. Okay, question, comments.
Can I a question here? The speaker mentioned CP asymmetry. Somebody talks about a Belle II now, CP asymmetry.
Do you mean CP? Okay, CP violation in tau decays. Hello?
But
Yeah,
somebody
so.
talked a workshop here from Belle II.
Yeah. Okay. Yes, that is within the prospects for the future. Can be discussed later, but I can just comment that it's part of our program. However, there are still some studies on the performance which are required in order to achieve a measurement of this nature, of this asymmetric nature in the decay of the taus. But for sure, it's in the program for being measured in the future.
Thank you. Well organized.
Okay. Alberto?
I try again. So it's just a comment. I advertise also the opportunity of measuring the tau branching fractions, the tau leptonic branching fractions, because they are currently the limiting experimental input for the lepton universality test.
Thank you very much. Yes, this is challenging, I would say, and it's also part of, I don't want to spoil too much, but during the LFU, there will be some discussion about the current status of the reconstruction of the leptonic decays, in particular of the ratios. But yeah, there is, of course, the possibility of measuring the branching fraction itself. But again, it's quite challenging and probably will be a second step study on this one currently being done.
Thanks.
Yeah, for sure. For sure, we take note of this, which is quite important.
Yes. Okay. Any other question, comments? Okay, if no more questions, let's thank the speaker again, Michelle. Thank you very much. Okay, now we